LSTMs, long short-term memory networks, can mitigate the vanishing gradient problem in an ingenious way when they are in fact explicitly focusing on this forgetting behavior, but they are also able to more explicitly retain memory. To understand LSTMs, let's first look at an RNN in general in slightly more detail. A generic, simple RNN would have an input, a hidden state that is fed back to the network itself for the next time step, and an output that can, in simple cases, be the hidden state itself. Now, the hidden state of the current time step is calculated as a function of the input x and the hidden state in the previous time step. In this example, this is just a simple 10H function. However, LSTMs improve in this simple layout in a number of ways. First of all, there is a memory cell value that's carried over through time like a conveyor belt, and there are some new gates that explicitly learn how to best manage this memory. Looking into our visualization in more detail, where each line represents a vector data flow, you see there are 4 different layers that are interacting here, and there is a distinction between the hidden state and the actual output. The cell state acts as a conveyor belt to which the LSTM can either add or remove information, depending on the gate layers below. In fact, these gates with their sigmoid functions are able to act as learned choices between letting nothing through in case of a 0 value and letting everything through in case of a value of 1. So let's look at the different gates that influence the hidden state conveyor belt, as well as the actual output. This first one shown on the slide is called the forget gate layer, and it comes up with a value between 0 and 1 that controls what exactly should be forgotten. For example, in case of a language model, the gender of the last subject could be remembered as long as the next word might have to be matched for gender. And conversely, the gender might be forgotten if the text starts mentioning a new person. Our next gate is the input gate layer that uses a sigmoid and the 10H function to decide exactly what to keep, and for those values what exact feature to calculate and keep. The 10H function makes sure that the value is between -1 and 1. So to continue the earlier example, this would be where we might store the actual gender. So how do these 2 gate layers, the forget gate layer and the input gate layer, come together? As you can see on the chart, first we forget everything that is chosen to be forgotten, and then we store the new inputs wherever applicable. Finally, let's look at the output gate. We read from the cell state via a 10H function to project the values between -1 and 1, and another sigmoid layer decides what parts of the cell state should actually be present in the output. So to reiterate, not all of the internal hidden cell state is output, only a filtered part of it. This allows the network to retain information that is not directly useful for the current output, but might be later. Here is an example from Andrei Karpathy of the outputs of a character-level RNN. This network learned to detect comments and quoted values above, as well as indentation below in this code, and red sections show the detected areas.